also experiencing this 120 volts, and I have resistor 3. Let's make this one a light bulb, which is also experiencing 120 volts. So let's say I have R1, R2, R3, right? Because we said lights can act as resistors, right? They control the flow of current. All three of these resistors are experiencing the same voltage, right? Because we said in a parallel circuit, these different branches, the current needs to be stepped back down in voltage across the only resistor it's traveling across. Now, let's say I have a total amount of current that is unknown. Don't know how much is going into this junction. But let's say I know that I have amperes flowing through resistor 1. Let's say I know I have 8 amperes flowing through resistor 2. And let's say I know I have 7 amperes flowing through resistor 3. So I know I1, I2, and I3, but I don't know I total. So how much must have gone into that junction before it all split up? Well, it's just going to be the sum of these, right? Because ultimately, 8 and 7 are going to rejoin here. So that'll be 15, and 15 is going to rejoin, right? This is 15 amps. 15 is going to rejoin 2 amps here, which means that my total current in the circuit must be 17 amperes. So I total in this case is I1 plus I2 plus I3, which is 17 amperes. Okay, so these are just some basic applications of law of conservation of charge in the context of parallel circuits. So we know the voltage is the same everywhere. We know that the current is additive. By the way, I want to make another note about that. If I am simply adding more and more resistors in parallel with one another, is it going to increase the amount of current being drawn or decrease the amount of current being drawn? In series circuits, we saw that adding more resistors increased the resistance and decreased the current. Right? In series circuits, we saw that adding more resistors to a circuit increased the resistance and decrease the amount of current. In parallel circuits, the exact opposite is going to be true. So in parallel circuits, the opposite of this is going to be true. In other words, because all of these paths are experiencing the same voltage drop in a parallel circuit, by adding more resistors, I'm only going to draw more and more current. So in a parallel circuit, adding more resistors will actually decrease the resistance. We're giving more paths for current to take. Adding more resistors actually decreases. This is counterintuitive. Decreases the total resistance and increases the amount of current drawn. I'm going to explain. I'm going to use an analogy. analogy I'm going to use is the hallways. Everyone who's traveling from one class to another is going to represent charge. And everyone needs to get to those classes in a very small amount of time, right? So everyone's got to get there within the 4 minutes. If we only have one pathway for everyone to take, right? Let's pretend we only have one pathway for current to take. It's going to be really hard for everyone to get there. So resistance will be high. But if we give people additional pathways to take to their classes, if we add an extra hallway and add another extra hallway, then everyone can get there quicker because there are less obstacles in their way. There's less obstructions to them getting there. So actually, by adding more pathways in parallel circuit, we are going to decrease the resistance and we are going to draw more current. Okay, so make sure you know this. And then I'm going to show you how you can calculate the total resistance in a parallel circuit. Okay. So, given the following information, where I total is equal to I1 plus I2 plus I3, and so on, in a parallel circuit. And V total equals V1 equals V2 equals V3. If I substitute in Ohm's law, V equals IR, in other words, I is equal to V over R. You don't need to know this. You only need to know the formula I'm going to get to, but I want to show you how to get there. If I substitute this in for I total, for I1, for I2, for I3, right? So instead of saying I total, right, I'm going to say I total is the same thing as saying V total over REQ, which is equal to, right, this is the same as saying I total, which is the same as saying I1 is equal to V1 over R1, which is the same as saying I2 is equal to V2 over R2. All I'm doing is taking Ohm's law and substituting into this formula. And I3 would be the same thing as saying V3 over R3. Now, something is going to come out of this. Because V total, sorry, I wanted a different color. V total is equal to V1, is equal to V2, is equal to V3. These all divide out because of this relationship. So, if these all divide out, I can replace this with the formula you actually need to know. 1 over REQ is equal to 1 over R1 plus 1 over R2 plus 1 over R3, depending on how many resistors you have. That is where this equation comes from. So you are responsible for knowing this equation, I total equals I1 plus I2 plus I3. This equation, V total equals V1 equals V2 equals V3, voltage same everywhere. And this formula, 1 over REQ equals 1 over R1 plus 1 over R2 plus 1 over R3. And this formula is going to show you that by adding additional resistors, you will decrease the equivalent resistance. Now, just a side note, how can I solve for the equivalent resistance if this is only going to give me the inverse of it? Well, how do I get REQ from this formula? How do I get REQ, or the total resistance, from this formula? Well, if this is giving me 1 over REQ, then I'm going to need to raise the answer to the -1 power. I'm going to need to take the inverse of it. So let's do an example of this. Let's make a theoretical circuit. Let's make this resistor 1. So let's make resistor 1. Let's just go 2 ohms. Resistor 2 will also be 2 ohms. Resistor 3 will also be 2 ohms, because I am super creative. Alright, so find the equivalent resistance. So the answer to this question from before that I forgot to write was, to get REQ from this formula, we're going to need to take the inverse at the end. Okay, so let's solve. So find REQ. Find REQ of the parallel circuit to the left. I want to make sure it's still filming because I'm a little nervous. 35 minutes in, we're good. We're gooch. Alright, so to find the equivalent resistance, again I'm going to use this formula, 1 over REQ equals 1 over R1 plus 1 over R2. We want to get all of our points, we're going to write all of these out. So now we say 1 over REQ is the same thing as saying 1 over 2 ohms plus 1 over 2 ohms plus 1 over 2 ohms. Well, this is a really easy one because we have a common denominator here. In other words, we really have 3 over 2 ohms is equal to 1 over REQ. So now all we need to do is take the inverse of this value. So let's do that. So 3 over 2 to the -1. And you get 0.67. So REQ is equal to 0.67 ohms. So the total resistance of the circuit that I drew right over here is 0.67 ohms. Let's pretend we added in a 4th resistor. So add another 2 ohm resistor in. I want to see, is this number going to get bigger or smaller? Well, again, in parallel circuits, the more resistors I add, the smaller my total resistance should get. So we should expect this number to get even smaller. So let's add one additional resistor, one additional 2 ohm resistor. In parallel. So really, rather than 1 over REQ being equal to 3 over 2 ohms, we could expect it to be 4 over 2 ohms. So we have 1 over 2 ohms plus 1 over 2 ohms plus 1 over 2 ohms plus 1 over 2 ohms. So in adding another resistor, let's see what effect it has on the resistance. 1 over REQ equals, now we have 4 over 2 ohms, right? Because we have a common denominator, which is good, so we can add our numerators up. But we need to raise this to the -1 power. Take the inverse, take the inverse. So obviously this is really just 2 over 4. So REQ now is 0.5 ohms. Did it get smaller like we expected it to? Yes, it did.